Okay, time for another video presentation, and this time around we're going to be talking about Newton's laws. You probably heard of Newton. Here's a picture of Newton under the apple tree, which has some significance in physics. And if you don't know what it is, I'm sure we'll talk about it in class. Before we get into these things, of course, we want you to come away with some things that are going to stick with you even after this class is over. So now what we're doing is we're talking about dynamics. So far, everything that we've done has been kinematics, and that's just been a description of motion. But dynamics is talking about the causes of motion, and now things start getting interesting here. So we should be thinking about a couple of questions here. What are we going to accomplish by doing this? Understanding dynamics. How can we symbolically represent this? And how will the idea of understanding what causes motion be able to help us predict motion? And that's what we should come away with on this one. Alright, so here are two pictures of Isaac Newton, and he looks very different here. I guess he's a little bit older here, a little bit younger in this one, so you know, we all change as we age, of course. But also I think with Newton, it's very interesting character, Newton, and very significant in the history of human beings. But Newton, and part of the reason I wrote the two Isaac Newtons here is although he's very well known for physics, he was also very interested in alchemy, which is more of a spiritual kind of thing, and not really a science. It's more, I would say, like the precursor of chemistry, maybe, because they were concerned with how different things would mix together. The alchemists would try to find ways of making gold out of things that weren't gold, which would have been a pretty good trick if they could have pulled it off. And Newton also, like I said, was an alchemist as well as a physicist, which a lot of people don't know. The other thing is I think that in this particular picture, the picture on the right, I think he looks a lot like the guitar player from Aerosmith, if anybody remembers that band, Joe Perry, the guitar player from Aerosmith. And that band has been around for a while. You might not have heard of them. So here's a picture to see if you agree with me here. There's Newton and there's Joe Perry. I think they look kind of a lot alike there. What do you think? Anyway, that won't be on the test. Alright, so we're going to get into the Newton's laws here. And first of all, I want to say that Newton's laws were already established and written about before Newton was born. Newton was born the year that Galileo died, and Galileo had pretty much laid out Newton's laws ahead of time. So I really kind of think of them as Galileo's laws a little bit, but the whole world thinks of them as Newton's laws, so we'll call them Newton's laws too. Newton recognized that he didn't come up with Newton's laws, and he had a pretty good quote about it, and you see it on the screen there. If I have seen farther, it's by standing on the shoulders of giants, and he was certainly referring to Galileo as well as others, but Galileo was a very significant figure there too. I'm a big Galileo fan, if that hasn't come across already. But this is what we do as human beings anyway. We build on what has been done before. So we don't have to reinvent the wheel every generation. We can advance where we are, take it a little bit further, and each generation seems to do that, and it's happening at a very quick pace now. Very interesting to see what the world will be like when you're my age. Okay, so there's a little background there. Alright, so today we talk about Newton's laws, and we kind of agree with them for everything that we're talking about. They've held up for about 400 years right now. But before that, human beings came up with all different ideas on how the world works. I guess because we're in the United States and we're sort of a Western culture, we go back to the ancient Greeks for a lot of our foundation of our learning here. But I do want to point out before I talk about the ancient Greeks' belief that this idea of figuring things out isn't a Western culture thing, it's a people thing. Wherever there have been people on the planet, they've been thinking about these things. And so we talk a little bit about the ancient Greeks maybe because of our Western culture background, but certainly in the East they were thinking about this. Wherever there were people, they were thinking of this. Today we look at things a little bit differently than the ancient Greeks did, so it's worth pausing a little bit to talk about it. The ancient Greeks, and Aristotle was chief among them, described things that were moving through the air as being natural motion. And they thought that everything had a natural place in the universe, and they had a hierarchy of earth, wind, fire, and what's the other one, Mr. Reese? Earth, wind, fire, and air. I sure did. All right, so earth, wind, fire, and air. and they thought that all these things, water would have been the other one, fire and wind and air are the same thing. But yeah, so they thought everything had a hierarchy, and earth was the lowest, and then there was water, and then there was air, and then there was fire. So they would explain the smoke rising up through the air, fire rising through the air, as saying that it was trying to go to its natural place higher up. If they dropped a rock, they would say the rock was falling through the air and then through the water, if there was water, to reach its natural place, which was the earth. And we look at things a little bit differently now, but that was their explanation for things where they couldn't really see a force acting on it. So there was no force at all recognized. They just thought that objects were trying to get to their natural position. They described violent motion a little bit differently than we describe violence now, but this is motion where you could see the force. There was a visible push or a pull where you could see what was going on. Another part of their belief was that an object's natural position was at rest. So they felt that if a rock fell, it would fall and then it would come to a stop because its natural position was at rest. Or if something was sliding across a surface, they would say that its natural position was at rest, and that's why it came to rest. No force was recognized. They also felt that the earth was completely still, and we know that we don't look at that now, but that was an interesting change in the way people thought. But for a long time and for most of human history, the major belief, the prevailing belief, is that the earth has stood still. Okay, so Newton's first law of inertia, well, here's a bunch of words that could describe it here, but the main idea is that an object is going to continue doing what it's doing unless we try to add a force to make it change what it's doing. So the word inertia means a resistance to change, and the idea here is that an object will move in a straight line until at a constant speed until something makes it stop doing that. And if an object is not moving, it'll continue not moving until something makes it move, and that's where the forces come in. So that's the idea of the law of inertia. Okay, so now with Newton we have a different view of motion. Now we're not saying that an object wants to come to a rest, we're saying a force has to cause it to come to a rest. And we're also not saying that an object is falling because that's what an object naturally does. We talk about friction for making things pick up speed or slow down, and we talk about gravity as making things fall through the air. So this is a new way of looking at things. Well, a new way 400 years ago, and it was pretty radical at the time. Okay, so mass, which is going to be a new variable for us here, a new piece of information that we're going to identify, is the amount of inertia. So the bigger the mass, the bigger the resistance to change. If you have a large mass and you want to get it moving, you have to supply a big force to get it moving, and it's going to resist your change a little bit more. And if it's moving, large mass, it's going to take a bit to slow it down. Alright, so mass is going to be measured in kilograms. So here's a new unit for us and a new variable as well, the mass. A lot of times people are going to confuse mass and weight. Mass and weight are not the same thing. Mass is the amount of matter that you have, and weight is a force you feel because of gravity. So 1 kilogram of mass weighs 9.8 newtons, and since Newton's laws are what we call these things, we give the unit his name. And weight is not the amount of stuff that you have, it's a downward force because of gravity. And we'll start talking about that in a couple minutes here. Okay, so the unit for weight and all forces really is the Newton. And the Newton is a derived unit, and it's derived out of the mass and also the meters and the seconds squared. So the units have to be kilograms, meters, and seconds squared. I'll show you what I mean about that in a minute. But here is a new formula for us. It's been a little while since we had a new formula, right? And now we're going to start adding formulas at a quicker pace. So the formula here is W is equal to mg, W is the weight, m is the mass in kilograms, and g is the acceleration due to gravity. And we know that's 9.8 at sea level on Earth. And unless we otherwise talk about it, let's just assume that we're at sea level on Earth, and Monroe is pretty close to being at sea level. And we're also on Earth, as you well know. Okay, so let's try it out here. What is the weight of a 1 kilogram object? Well, the weight is equal to the mass multiplied by the acceleration due to gravity. The mass is the 1 kilograms. the acceleration is 9.8 meters per second squared. Now I put the units in here because we can see the units would be kilograms multiplied by meters divided by seconds squared. But a shorthand way of saying that is the newtons. So we'll say here that the weight is 9.8 newtons. Alright, so again, this is derived out of kilograms, meters, and seconds. Alright, so there's an introduction. Hey, give this one a try. What is the weight of a 2-kilogram object? Well, you would take that mass of 2, right? You'd identify your variables, of course, multiply it by 9.8, and 19.6 would be your answer. Let's try out a couple more here. What is the weight of a 15-kilogram object? Give that a try. I'll pause here and take a sip of coffee while you go and look at that. Delicious. Jamesburg, my coffee mug. That's where I live. Hey, Jamesburg, right down the hill. Alright, so hopefully you got an answer of 147 newtons. There you go. And let's try another one. How about what is the mass of a 100 newton object? Well, 100 newtons is the W. W is equal to mg, so if you divide that by 9.8, you should come up with 10.2 kilograms. And if you have any questions on this, please bring them back to class and we can talk about them. Alright, so how about this one? Same kind of a deal here, just make sure you can get the right answer. The answer I got was 25.5 kilograms. And now you have some good examples in your notes to go back to when we start solving some of these problems. Okay, so how about it? What forces are acting on an object that is sitting at rest? Well, let's talk about it a little bit. One thing is there's always going to be weight acting on an object. That is the downward force due to gravity. So anywhere you are in this universe, you're going to feel some kind of weight. And at Earth, we feel our weight. It's kind of hard to jump off of this planet here because our weight is always going to drag us back down again. But there's another force here, because if I put an object sitting on a surface, it's going to have the weight pushing down, but if it was just the weight pushing down, then the object would be moving down. But it doesn't. If it's sitting on a surface, there's what they call the normal force, and that's like a supporting force that is going to push back up in the opposite direction. And that should make some kind of sense. And normal is a word for perpendicular. So if the surface is flat like this, the force acts perpendicular to it, and that's the meaning of normal there. Okay, so if you have an object that is sitting on a flat surface, untouched or otherwise, the normal force and the weight are going to be equal but in opposite directions. They're going to balance out. So the weight pushing down will be balanced out by the normal force pushing up. So that's the idea of the normal force. Okay, so let's see what we got going on here. Oh, and by the way, for our class, we're going to always assume that the normal force and the weight are equal to each other. For our class, we'll assume that. All right, so now we'll talk about net force. And net force is the idea of how do all the forces add up together? What's the overall force? I kind of think of net force like net pay if anybody's getting a paycheck. You get your gross pay, and then they take out your taxes, and what's left over is the net force. So if there are forces working against each other, the net force is what's left over, what's available to cause the motion. Okay, so there's at least one force acting on an object at all times, and again, the net force is the total of all of these forces when you take them all into account. Okay, so if the net force and the weight are equal to each other and the object is sitting on the surface, what's the net force? The net force will be 0. There'll be an upward force counteracted by a downward force. The net force is 0. Okay, so all of the forces are measured in newtons. It doesn't have to just be weight. So here's an example of a tug of war. You can see these little kids, and they're pulling on the rope. So if the team on the left pulls with 1,200 newtons and the team on the right pulls with 1,000 newtons, what's the net force? They're working against each other. Can you see that? It's kind of like a vector problem, really, and forces can be added as vectors, so it's worth pointing that out at this point. Did you come up with an answer there? This is a pretty famous tug-of-war match. The answer, of course, is 200 newtons to the left, but this went on for years. You can see those little kids grew up. Went on for years. I don't know how they fed them, but, well, who knows? That's not for us to think about. We have other things to think about. Okay, so forces, as I said, can be added as vectors, and you can picture that. And think of your head-to-tail diagrams, too, when you're thinking about forces and vectors. And we're going to apply the vector concept of forces. Okay, so what they do to talk about the forces acting on an object, we've talked about head-to-tail diagrams, but they also have what's called a free body diagram. And a free body diagram will identify the forces that are acting on an object. So here you can see the normal force pushing up, the weight pushing down, we got the applied force and the force of friction. By the way, it's the direction of the arrows that matter. Sometimes they'll put weight down here, but just so long as the arrow is pointing downward for weight, you've got a good representation of that force, and we'll see that in an example coming up. Okay, so just to give you an idea here, and that was one of our questions on how this could be applied to the real world, these free body diagrams are used to talk about a lot of different forces here. And human anatomy, they'll be talking about that. They'll be doing it for sporting events, for designing different, well, here we have a helicopter and we're trying to figure out the tension going on. So these are widely used and with a lot of success. So ours are going to be very basic free body diagrams, but just so you know, they're out there and they are widely used. Okay, so equilibrium is a situation where all the forces are balanced out to zero, and that means that the net force is going to be zero when you're in an equilibrium position. Hey, how's it going? All right, so the net force is zero at an equilibrium position, and here's a bridge. That's the Tower Bridge in London. Some of you might have seen that before. And how about it? Lots of forces are acting on a bridge, right? What are those forces? Well, there's the things that are on top of the bridge pushing down. There is the weight of the bridge pushing down. There's the support forces pushing up. You want all these forces to be basically balanced out to zero, or close to zero anyway. You don't want too much sway in your bridge. Is anybody afraid when they drive over a bridge? I know some people are, right? And they're afraid of that idea. Because well, what is going to happen if the forces there become out of equilibrium, too far out of equilibrium on a bridge? Your bridge is going to come down, and that's a problem. And we have some concerns here in the United States. Some of these bridges are old, and they're structurally not as secure as we'd like them to be. Okay. So how about this one? Here's an interesting question. Can you be at equilibrium? Can all the forces be balanced out to zero and you are still moving? Well, how about it? Turns out the answer is yes, because that law of inertia that we talked about, unless there is an unbalanced or net force, an object will keep doing what it's doing. So maybe for a car driving in a straight line, the force of the engine is equal to the resistive forces, and there you move along at a constant speed. So yes is the answer to that one, if all the forces are balanced. Once they become out of balance, that's where you're going to have things slow down or change speed or direction. And an air hockey table is a good example of that. Pushes along until the forces become out of balance, and we get a change in where the puck is going. Okay, so here's a free body diagram practice for you. If the body is at rest on a table, we're going to draw a diagram of the forces acting on it, right? So we'll always be dealing with a box here. So what do we got? We got two forces. One is going to be pushing down and one is going to be pushing up. The normal force with the arrow facing in the up direction, and then we have the weight balancing it out. By the way, these are tricky until you get the hang of them, but for free body diagrams, you should always start with the normal force and the weight, because for our class, they're always going to be there and they're always going to be equal to each other. Okay, so again, the normal force and the weight are always acting on an object. Even a house of cards. That's a pretty clever design right there. Okay, so just when your free body diagrams, I would start with those two forces and then see what the other conditions are. Let's try another one. How about if a person pushes a box to the right, then what are the free body diagrams going to look like? Well, as I've recommended, start off with the normal force and the weight. They're going to be there every time. If a person is pushing a box to the right, we'll call that their applied force. So here's my applied force with the arrow going to the right. But I got one more force here, and I want to identify that. And do you know what it is? What is the force? If I supply a force to slide something across a surface, what's working against me? If you said friction, you are correct. Friction is the force working against you. And anytime you are sliding something across a surface, friction will be working against you. It's always an opposite of the direction of motion. Well, that's it for this video lecture. Hope you found it informative, and if you have any questions about it, please bring those questions back to class. Thanks for listening. Look forward to seeing you there.